Thank you very much for the invitation. It's a great honor to speak here at a conference that is honoring Damien. And so there's this saying that almost every mathematician only knows like 2 or 3 tricks and makes his or her career out of it. And I can really say this is true in my case. And one of the tricks I definitely learned from Damien, and I used it over and over. And this is about like the flexibility that you get by viewing the group ring inside the cross-product ring. And you write many papers and they look all very different, but there's like a basic trick that you use over and over and over, and this is the case. But I don't want to bore Damien, and so I'm talking about a work that uses another trick, maybe my second trick. So this is about higher property T. And I know that some of you were at this summer school, IGS summer school a few weeks ago, but this is about something that happened after. So it's relatively new, and this is joint work with Saar Bader, Jacquet Bader, and Uri Bader. And let me, because this is so long, just call them Bader. Okay, so these are Uri's kids. Jacquet is a PhD student with David Kielak in Oxford, and Saar is a master student of mathematics. And the history of this project I'm going to talk about is actually that Saar and Jacquet had an idea to tackle a question about higher property Fa, which I will talk about. And somehow this started this whole project, which is somehow an extension of an earlier joint work I have with Uri on higher property T for unitary representations. So somehow the motivating question or slogan I want to start with is we have property T, Kazhdan property T, and some groups are more T than others. And there are many instances of this phenomenon. I think there's a kind of scientific consensus that higher rank lattices enjoy like the most strong version of property T, but you can somehow make this precise in many contexts. For example, certain rank 1 groups do have property T, but they have a kind of Hagerup property for LP spaces for very high P, which is somehow you could view as, okay, this is not the strongest form of property T they should have. And this is different for higher rank lattices. And there are many, many examples. Let me give you 2 instances where you see that some groups, and in these 2 instances, it will be higher rank lattices, have more T than others. Okay, so one instance is expanders. Or maybe, let me put it there. Still have to learn this. I know the professional practices before, but so expanders. So let's say gamma is a property T group. Assume that gamma is residually finite to make it more interesting. And then it's a classic theorem of Margulis that you get expanders out of it, expander graphs or family of expander graphs by looking at quotients. But I want to formulate a little bit different in a form that might be a bit unusual. I want to assume that gamma has a finite classifying space. It's totally stable. Right, so there's this contractible space in which gamma acts freely, and finite just means co-compact, so finitely many orbits of self. And then I want to express it like that. If you look at the von skeleton of this thing, which is a graph, and you look at the quotients by finite index subgroups, then this is a expander family. And since it's just for context, I will not define it. Now, what about groups that have a stronger property T, like certain lattices in higher rank groups? Well, there is a theorem that was published in 24, so it's relatively recent, a breakthrough by Efra Kaufman, that this is about lattices in higher rank non-Archimedean groups. So let's just say we have something like SLNQP. And then that n-1 is the rank of this group, and if you look at the n-2 skeleton of a classifying space, and actually you could take the Gruer-Titz building in this case, then this is a higher dimensional expander, whatever that is. And somehow, this is a theorem about these specific groups, but somehow what is behind this is something that these groups enjoy, and which is a kind of, it's very much related to property T. So what is really behind this is a mod 2 version of higher property T in the sense of Garland. So you can't strictly say this is a stronger version of property T, because this is a mod 2 version, so it's more like a modification of something which is supposed to be stronger than property T, but it is very much in this spirit of this slogan. So this is one instance. Another instance is actions on low-dimensional manifolds. So I also want to start with a theorem that is about every property T group, and this is a theorem of Navas. So if you have a property T group and it acts on the circle in a following specific way, so if gamma has property T, and you act on the circle by diffeomorphism. Maybe I express it like this. You have a homomorphism. So this is a technicality. It's not important for us. You have an action by diffeomorphism. There is a certain Hölder condition, Hölder continuity condition on the differentials, which is expressed by this superscript. Don't worry. But then such an action given by a homomorphism has finite image. This theorem is about any property T group. And now also here, there's a strengthening as soon as you get to groups that are supposedly have a stronger property T. And there's this breakthrough, which is completing conjectures, but also results. So of Gist and Witte-Morris. And this work says that you actually don't have an action by homomorphisms in a higher rank case. So this is the theorem. Just spelling Deroy-Gourtado. Also very recent. So if gamma, let me just be a bit quick and say if gamma is a higher rank lattice, then any homomorphism, and now you go to the group of homeomorphism, has finite image. So strengthening of this theorem, there is one difference as far I'm not like an expert on this work, but as far as I can tell, and you can correct me, it's not like here that there is like an abstract notion of some stronger form of property T behind that would imply it, like here. So it's really about working with lattices all the time. So that's a small difference. And another thing I should say that maybe even more important, the way they did use it is by proving that you actually cannot work on the real line, and by that proving that these higher rank lattices are not left orderable, which is maybe even more important. So let me say this. So similar for actions on the real line. So in particular, these groups are not left orderable, which is an open question for Kazhdan property T groups, whether there exists left orderable groups that have Kazhdan property T. I would say probably yes. Well, I mean, who knows? But for these very strong property T groups, higher rank lattices, they show that it's not possible to have like interesting homomorphisms, and therefore they're not left order. And so this theorem here is kind of the topological Zimmer program in the smallest dimension that you can imagine, dimension 1. It's about homomorphism on one-dimensional manifolds, non-compact and compact. If you add a little bit more regularity and again talk about diffeomorphism, there is this famous work of Brown, Fisher, Hurtado, saying, maybe let's just state it for SLNR. So I have a lattice in SLNR. And then now, if you have an action given by a homomorphism from gamma to diffeomorphism, C2 diffeomorphisms of M of a compact manifold, compact smooth manifold M of dimension smaller than the rank, and the rank is n minus 1, then this has finite dimension. Okay, so this is like the topological Zimmer program if you want dimension 1. This is with more regularity, and it only allows for compact manifolds, but there you can allow for higher dimensions. And here, I mean, one part of the proof was also a strengthening of property T. I'm not saying this is like the only thing that matters, but somehow a crucial ingredient was what's actually called strong property T for these groups. A notion by Lafort, and this relies also on work of De La Salle and Delatte. This is a strengthening of property T I'm not going to talk about, which is about allowing for non-unitary, non-isometric representations. But it is an instance of this slogan, so that some stronger form of property T, and here you can isolate it somehow, gives you strengthening of theorems that you have somehow just for property T groups. Okay, so what I want to do in my talk is, there's a reason I put these two instances on the board. What I want to do is I want to talk about higher property T. I mentioned here this mod 2 version. We will talk about the ordinary higher property T version. And I will talk about an application of higher property T in a context which you could describe as the simplicial version of the Zimmer program. And the higher property T that I will talk about in the end, the thing that I need is something about Banach spaces, not just Hilbert spaces. But let me first tell you what I mean by higher property T. So there is kind of obvious generalization or notion of higher property T as soon as you have a theorem by Delorme and Guichardé. Yeah, let me maybe put it down. This is a well-known, probably most of you know it. So if G is a locally compact, let's formulate it also for topological groups, sigma compact topological group, then G has property T in the ordinary sense if the first cohomology, and if you talk about continuous groups, you want to add continuous cohomology, vanishes for all unitary G representations. Right, so vanishing of the first cohomology with unitary coefficients, that's the same as property T. And you might, okay, without proof, but this is not hard. You can also show that this is equivalent, this vanishing is equivalent if you only have it for all unitary G representations V that have no invariant vectors. So if you only have, so Vg is the subspace of G invariant vectors. If you only have the vanishing for that, then it implies also the vanishing in general. Now this gives you an obvious way to generalize property T, and there were like versions, slightly different definitions of higher property T in the literature. There is one by, well, help me, Andreas, your work with Alex Lubotsky, Oren Becker, and de Chiffre, yeah. And then there was also a paper by Piotr Nowak and Uri Bada, and there are like small differences in this, but here is one definition that I want to discuss. Let's say a locally compact group. Let's do it for topological. So it has higher property T, but now there are two, also here I want to discuss two flavors, two versions. So there is, let's call it Tn with this kind of brackets. So it has this kind of higher property T. By definition, if the homology vanishes for indices or degrees up to n and every unitary G representation. And let's say we have property Tn with the round brackets. If the same thing holds, but I'm only requiring this for unitary representations that do not have invariant vectors. Okay, so this is, if you have n equals 1, it doesn't matter by what I said. It both gives you the ordinary property T. If you go to higher degrees, it actually matters. So there's a difference between whether you allow the trivial representation or not. Okay. And then the higher property T in Galan sense that I mentioned in this theorem of Efra-Kaufmann is, let me just state it for SLNQP. So SLNQP and all its lattices have, so the rank is n minus 1, and it goes up to n, the rank minus 1, so n minus 2. So these non-Archimedean groups and these lattices in these non-Archimedean groups, they have complete vanishing even for the trivial representation up to this degree. And with Uri, I proved the analogous state. So this is with Uri Bada. We proved this for the Lie group case. Sorry, wrong brackets. Because that was the point I want to make, that SLNR, and if you look at the lattices in SLNR, they do have interesting cohomology also in low degrees for trivial coefficients. And actually, this is to have this kind of property T actually helps to improve stability theorems for the ordinary cohomology.
Right. Why you don't look some different
Why I say mod 2?
yeah.
Well, okay, I was sufficiently vague, but they look at the chains over the finite field F2, and they have to formulate a certain expansion of the differentials using the Hamming distance that you have in Galan setting for the differential of the real chain complex. And so you formulate it in a way that doesn't use the Laplace operator, and it doesn't use somehow positivity or something, but you can formulate it in terms of just the differential, the Hamming distance, and F2 coefficient. That's what I meant by a mod 2 version of Galan's theorem. And it's very hard. It's not like you modify Galan's proof a little bit. I mean, this is a hard theorem to do this. Okay, so this is higher property T, and I promised you that I want to talk about somehow a simplicial version of this situation. So actions on low-dimensional manifolds. What is the simplicial version of that? And this is something which is also well known in degree 1. So let me call this subsection higher property Fn, Fa.
Yes.
So what is Fa before we go to higher? This is a reminder. So a group has property, sometimes also called Serre's property, Fa, if every isometric action of gamma on a tree has a global fixed point. Which is equivalent to having only bounded orbits. Now, it is if you have Fa, so for example, you get these actions from splittings as amalgamated free products, and there's this theorem that Kazhdan property T implies property Fa. I didn't put, it's Vatat, my spelling is probably, it's wrong, right? Vatatani. Vatatani. Thanks. So the theorem is that property T implies property Fa. So this is a very nice geometric consequence of property T, and totally lost track about the time now because we started late, but maybe I give you at least, not a proof, but at least somehow the idea how it relates a little bit. And again, I assume that many of you know this, but somehow if you have an action on a tree, let's call it the tree T, without fixed points, then if you want to use this characterization of property T, you want to construct a one cocycle that does not vanish, right? Because we're showing the contraposition. So you want to write down a cocycle, one cocycle, and the one cocycle is realized on the L2 space of the oriented edges. So oriented edges of the tree, and so the cocycle maps gamma to the characteristic function of, you choose some base point and you do something like this. It's a difference of characteristic functions of finite sets. These are the geodesics. And this, you have to check, of course, that this is a one cocycle. And if you have unbounded orbits, it's very easy to see that this cocycle is actually not zero in the first cohomology of this representation with the obvious action of gamma on the edges. So, okay, so I have to prove it's a cocycle, I have to prove this, but it's a very nice short proof. And I want to say one thing, the L2 here is a kind of a red herring. Okay, you want L2 because you want a Hilbert space, you want to apply somehow this characterization, but in some sense you could also work with L1. It doesn't really matter. So this would also be non-zero in L1. Since this is a characteristic function of a finite set, it's also somehow that this is not so important. It's only important then in this characterization. Now, we have a higher property T very easily by having higher cohomology. What is the analog of property Fa in higher dimensions? So this is a concept that was introduced by Benson-Farb. Maybe I put it here. So he suggested a higher analog, saying a group. I mean, you could also discuss topological groups, but let's stick with discrete groups for now. Has higher property Fa, so let's call it Fan for natural number n. If every isometric action of gamma on an n-dimensional ket0 complex has global fixed point. And there is kind of, you are basically, so here I said isometric, but if you have some branching in the trees, this means simplicial, and there is a similar phenomenon here. So you could also just do this definition for simplicial. This is really about, more about complexes and simplicial actions. And so what Benson-Farb proved was something, again, in the spirit of the slogan. He looked at SLNZ, the lattice SLNZ, and he proved something which is stronger than what you would only get from property T. He proved property Fa n-2. So this theorem by Farb that this group has Fa n-2. You always see it's always the rank -1. And there are many theorems in the literature that have this kind of threshold. He only proved SLNZ, and he used unipotence in a very essential way. So this is definitely, his proof is a proof that wouldn't work for arbitrary lattices in SLNR. Then, like a year ago, there is a very interesting, very fascinating, inspiring paper by Ben Lohe and Mikołaj Fraczyk, where they used, quite heavy methods from, I would say, geometric measure theory and minimal surfaces to prove somehow, oh, maybe I I put it here. So there is a conjecture. I mean, Benson conjectured this, that all lattices in SLNR, and again, I could talk about semi-simple Lie groups. It's just for simplification, I formulate it like that, have property Fa n minus 2. So there's this conjecture, and then I think it was a year, maybe it was 2 years ago, I forgot. There is this very interesting work by Lohe and Fratschik, and they prove that co-compact lattices in SLNR, so the ones that are somehow the furthest away from this having unipotence, they don't quite prove that, but they prove Fa n over 8, or yeah, something, n over 8, with very geometric methods.
King.
Can you read it?
8. N over 8.
N over 8. N over 8, yeah. Yeah, it's hard to read. And somehow this was the starting point of what we want to do. And now I think I have to clean this a little bit.
So, big. Meaning established.
Yeah.
And passport doesn't have to pay to you other than had finger and me. If we buy then test it.
Other non-uniform lattices?
But for the publisher.
Yeah, but it's about this Q split case. Yeah. So it doesn't have to be SLNC or it doesn't have to be SLNR, but it's like his method, or maybe I could say it like that. His method goes up to the Q rank, but the conjecture is up to the real rank. Yeah.
Oh wait, what about what way by them? So I mean that believe that's potential student in the black shops but about home. But it's a Julian that he could talk in. He did go.
So definitely can't be n, right?
Yeah.
N minus 1 is maybe not so clear. Yeah. Let's also clean this. All right, so let's talk now about the third section, and this is about higher property T for Banach spaces. Higher property T for Banach or Banach representations. And well, the definition is kind of, I could have done it right away. Let me define this round bracket higher T. So we say, and again, you could do this for locally compact groups. You can do it for discrete groups. So P is a parameter from 1 to infinity, excluding infinity. And we say that G has this property T if for every linear isometric G action if G is locally compact, some continuity is also involved on an LP space. And LP space, you could say it more abstractly, but the LP space is just LP of a measure space. Since we have round brackets, I want to assume that there are no invariants. Satisfies that the cohomology with coefficients in this Banach module is 0 for degrees below or equal n. Right, so it's really exactly the analog, but instead of a Hilbert space, we allow certain Banach spaces. And the starting point of our project was actually the application, not the theorem in the end. That's, I find definitely as interesting, but we started somehow, or I should say Sarah and Jacquet actually started thinking about an application. And I mentioned here that L2 was actually a red herring, and you could have talked about L1, but it turns out that in higher dimensions, this is actually important. So the theorem is that if your group, let's talk about discrete again, if gamma has Tn L1 for L1 spaces, then gamma satisfies Fan. So it's not an application of the unitary higher property T. That was actually a question that Benson Farb also asked us a while ago, whether the unitary property T implies this. I mean, I don't know. I don't have a counterexample, but somehow it seems that the essential thing is to have higher property T for L1 Banach spaces. And then you have this implication. And let me give you, so how much time do I have? I lost track. Oh, I have 10 minutes? Okay. Then, no. Then I will shorten this, and I will just say that the proof consists in considering the following double complex. So there is that's the only thing I will say, there is a double complex. You can look at if you want, the usual chain complex of your preferred chain complex of your group gamma. And now you plug in as coefficients the L1 completion of the simplicial chain complex. Of X. This is the space you're acting on, right? I should have said it. So you have an action of gamma on X, like in this situation. And actually, I want to make the following. The cat 0 is also a red herring. And actually also in this work, they prove something more general. Maybe if you want, you can call it HFAN for homotopy Fn, where you just say contractible instead of cat 0. For tree, it's the same. A contractible one-dimensional complex is a tree. And actually, you can do this. And cat 0 is not even needed. So this is a double complex you look at. You assume gamma acts on X. You assume that, I should say finite orbits then. Okay, the one thing where you need ket 0 is to go from finite orbits to fixed points. All right. But if you do that, you assume you have such an action with unbounded orbits, and then you consider this double complex with coefficients in L1. So you have this direction of the differential, and you have this direction of the differential. And somehow the contradiction that you get by assuming Tn and assuming that you have an n-dimensional complex with unbounded orbits, what is the contradiction that you get in this proof? Well, you use the assumptions to show that the total homology is 0 on the one hand, but you use another method to show that it's non-zero on the other hand, and that's the contradiction. And somehow the reason you want to have L1 is, first of all, there's no locally finite assumption anything on X. So you have to think about that you actually can L1 complete this chain complex. You can do it with the L1 norm, no problem. It's more problematic with L2, but with L1 you can. So this is one instance where you use L1. And the other instance is that very essential thing that if you have, if you look at the L1 zero homology of X, it does not vanish because you have an augmentation on L1. It's also something you don't have with L2. So these are the two things, very little things. It's a very formal proof, but it gives you a contradiction under this assumption, and it proves you this homotopy FAM. Now, after we realized this, we lost a little bit hope because we needed this L1 Banach property T, and very little is known. Essentially, what was known was the degree 1, where we have FA anyway, so there is nothing new there. But we're very happy that we recently managed to, let me put it here, to prove a version of that for lattices. So let gamma be an irreducible lattice. In a semi-simple Lie group. G, finite center. Let's look at the Banach representation. So let this be a linear isometric action. On an LP space V, LP Banach space, where P is something between 1 and smaller than infinity. And let's say without fixed points, otherwise wouldn't be true. And then you have this vanishing. I just formulated out again for I below the real rank of G. So that is that gamma satisfies this TLP R minus 1 LP, and R is the rank. And of course, then as a corollary of this theorem, you get the an yes answer to Fab's conjecture. With the optimal bound. But I would like to stress that another corollary which is interesting is that it answers positively to a question of Gromov. So in the situation of Farb's conjecture, the interesting case is where you have infinite isotropy. But the case where you have the regular representation is also very interesting. Oh, I should also say similarly for G. So I didn't. So what you have is this vanishing of the LP cohomology below the rank. And actually also for lattices. So this is a question that was studied a lot, and somehow the foundational work, first results are due to Ponceau. Then in degree 1, there was a huge study by Cornelier and Tessera. Maybe I put some names here, previous work, because there was already quite some work on this. So Cornelier and Tessera, they not only studied the simple, semi-simple case, but also other connected Lie groups. Then Bertrand Remy studied a little bit more the other side of this question, like the non-vanishing and what happens in the rank, but maybe let's put it here. Yeah, I should change the order. And then the first result in higher degree was achieved by Lopez Neumann, who did and considered the degree 2 case. So that was the first result that somehow went beyond the degree 1. But at least in many cases, not in all, but in many cases. But this is now completely true below the rank of the group G. So let me, I now have 5 minutes or so? Not really? Let me say a few words. Let me say a few words. So what was the challenge somehow? We had this result about higher property T for unitary representation. So somehow, what is the challenge in this? The challenge was that in this work, in this previous work with Uri, we very much used the results of Wogan-Zuckerman and Borel-Wallach. And these classical works are about Lie algebra cohomology, and they give you vanishing below the rank of G for irreducible representations. And that was an input. This was like a black box we inserted, and then we had some technology to boost this to the general result. So that is gone, right? If you talk about Banach space representations, there is no decomposition into irreducibles. So somehow the challenge was to find global method to prove higher property T. Like for property T, we have many of these methods. Of course, you could prove Kashtan property T for quaternionic hyperbolic space by looking at the Lie algebra cohomology of irreducible representations. You can, but you don't have to. There are global methods. You can look at the book of Becker and Valette to see how it goes. And this is somehow how we deal with property T. We prefer somehow dealing with a Hilbert space and not decomposing it and using these very algebraic methods. And somehow that was a challenge. You have to find a method that avoids this decomposition. And the way to do this is to exhibit a certain action of G and also of gamma on a simplicial complex that allows you to run an induction over the degree, over all semi-simple groups and their lattices. We run an induction over the rank, and we use an action on a simplicial complex that allows this. Now, this action or this complex is similar, but it's different from the Tits building, the spherical Tits building. There is something called the opposition complex, which was used first by Ruth Charney in the context of homological stability, where they take the TITS building, and somehow your n-simplices are of this kind in the opposition complex. So there is the n-simplex in the TITS building, and then you take any opposite simplex in the TITS building. And this gives you a complex which is different from the circle TITS building. And the difference is that the stabilizers of this are, the stabilizers in the TITS building are parabolics. And now the stabilizers are intersections of parabolics and opposite parabolics. And these are Levy groups. But the Levy groups are reductive. So somehow you run an induction over the rank of reductive groups. That's one aspect. There is another aspect that you have to prove new theorems. This is somehow where the function analysis. This is more like topological, but there's also a part where the function analysis enters more strongly, and this is about dealing with product situations, dealing with product of groups, because these reductive groups, they decompose as semi-simple group of lower rank, to which you can imply the induction in a torus. And somehow you have to deal with this product situation, but this can be done in the Banach situation. And then you can somehow use this opposition complex to run an induction. So this is somehow the new input, and that avoids, somehow using algebraic results about representation theory. And I end here. So thank you.
Yeah.